Welcome to part 4 of the videos or series of videos that I'm making on passage planning. The first part dealt with the appraisal process of the passage planning. The second part dealt with the planning process of the passage planning. The third part talked about the reporting procedures. And in today's part 4, I'll be talking about tidal clearances and underkill clearance and squat and what principles or factors should be taken into account when planning for a vessel's passage regarding these. And now I've given the links to the previous parts in the description section below, and you may also find some other videos regarding chart work and coastal navigation that you may find useful. So let's get started with part 4 of this video. So like I said, part 4 will focus on the following. Uh, we have the concept of the underkeel clearance or UKC. We'll talk about squat. We'll talk about calculation of tidal windows, and also what is the principle of MDR, which is the minimum depth required. So let's get started. So before we go deeper into this, you must understand the meaning of each of these terms, and that's why I have shown this diagram here on your screen, which will help you to understand the meaning of these different terms with respect to a vessel which is floating at sea or which is in berth. So if you see here, you can see firstly you should be starting from the top of the figure. So you have the horizontal line of the water level that shows the water level there. So in respect of the water level, I will explain the rest of the terms to you. So the first term I will explain is the draft. So the draft is of course the distance from the water level to the keel of the ship. That is the first term. The second term I'll talk about is the datum level. So the datum level is the average height of water, average height of tide experienced in a particular area. So you may have high tide and low tide, and then you have the average height which is experienced in an area. That pretty much in layman's terms, that is the reference to the datum level. And with respect to the datum level to the water level is what you get your tide height. So if you see on the left side of your screen, you have the tide height label there. So the tide height is from the average level of water to the water level currently as the height of tide or tide height. Then of course from the sea bottom to the water level you have your charted depth, that is again to the extreme left of your screen. And then you have your just below the vessel you can see that you have the static underkill clearance. That refers to the depth of water available under the keel when the ship is stationary, when the ship is not moving, when the ship is in port. It could be in berth, it could be in anchorage. And then you have your dynamic underkill clearance, which refers to the underkill clearance or UKC, as I will be calling it UKC, of the ship. That is the depth of water available below the ship when the ship is moving. If you notice here, you can see that the dynamic UKC is less than the static UKC. And that is because, as I'll explain later on in the slides as well, that once the ship starts to move, when the ship has some speed, it experiences something known as squat. So basically the ship sinks. I'll talk about it more as we go deeper into the video, but because the ship sinks when the ship starts to move, the underkill clearance or the UKC reduces, and that's why the dynamic UKC, that is the UKC of a ship when the ship is moving, is lesser than the static UKC when the ship is stationary. All right, so naturally the shift between the dynamic UKC and the static UKC gives you the allowance for the vertical ship movements, which is referred to as squat. And the squat is affected, of course, by the ship speed. The higher is the ship speed, the greater will be the squat, and we'll talk more about it. So I think I have covered pretty much most of the terms associated with it. So we'll start firstly with the UKC, and which stands for the underkeel clearance, as we have known before. So as I told you before, that maneuvering of a vessel is affected when the static UKC is less than 7 times the draft. That means we are in shallow depth or shallow water. It will become noticeable when it is at 4 times the draft. Alright, so when the static UKC is 4 times the draft, it starts to become noticeable, and when it is less than 7 times the draft, so we say that that is the indication that the vessel is now in shallow water. And when we say it's in shallow water, the vessel is basically starts to experience the principle of squat, because of which the maneuvering of the vessel also starts to get affected, and there's always the danger of the vessel's bottom touching the seabed or the propeller or the rudder getting damaged. So all those things come into play. And I'll show you what I mean. I'll show you some diagrams as well. So squat is when any vessel, when moving through the water, develops a tendency to sink deeper into the water as speed increases, and this is more pronounced or more noticeable in shallow water. Masters of the ship normally nominate a safe under-keel clearance to be maintained at all times during a voyage. Now remember, if we go deep into it, the nomination of the under-keel clearance by the master may vary slightly depending also on the situation that your ship is in. Like I said, I think in my previous videos I mentioned this, that sometimes in river passages there will be times when you may have to go with as low as 50 centimeters of UKC, which is normally not liked by the masters. But because it's a river passage, sometimes you have sandy bottoms or shallow sandy seabeds made of sand and soft material, where it's even allowed for the ship to touch bottom. So of course there are different situations, and as a master you will have enough experience to understand in which situation you may allow a much lesser UKC. But normally master would like to have a minimum UKC. They like to have a safe UKC to keep the ship's propeller and the rudder safe and the ship's bottom from touching the seabed as well. If there is no UKC nominated by the master, then the rule of thumb is that at least 10% of the ship's draft should be maintained in depth of water below the keel. So if your draft is 10 meters, then at least 10% of 10 meters is about 1 meter. So 1 meter of UKC should be maintained below the keel. So 1 meter of depth of water should be available under the keel. So that is normally the rule if the master does not nominate a rule himself or herself. The squat may be also calculated by using the formula, and the formula is squat equals V square multiplied by block coefficient. So CB is block coefficient divided by the constant number 100. So CB, like I said, is the vessel's block coefficient that you may obtain from the vessel's maneuvering data, maneuvering diagram or maneuvering booklet, depends on what it is called in your ship. The V is of course the vessel's speed through the water in knots, and 100 is of course a constant. This formula is also valid for open waters, and in shallow waters the figure that you get is normally doubled, because that gives you a safety margin. All right, because like I said, in shallow water the danger of squat is more. In shallow water the danger of the ship running aground or running or touching the bottom is more in shallow water, more profound in shallow water. So you need to double it, which will give you an adequate safety margin. So you can see here in the figure, this graph, the speed is marked against the squat. So you have the squat on the y-axis. This is also known as a squat curve, and you have the vessel speed on the x-axis, on the horizontal axis. And you can see here that as the speed is increasing, you can see the value of the squat is increasing as well. For the purposes of this curve, the block coefficient used was a figure of 0.85. Why this is important is basically the block coefficient figure tells you whether the vessel is a full formed vessel or a fine formed vessel, and I'll talk about that as well later on, how this impacts the squat experience by the vessels. But here you can see that as your speed will increase, the squat will also increase. The reason for this is, if I can explain it to you quickly, is that as the vessel moves faster, the water beneath it also starts to move faster. Now, because of this fast movement of water under the keel, there is something known as Venturi effect. The Venturi effect is actually a suction effect. So as the water moves very fast under the keel, there is a vacuum created, and that vacuum, because of the vacuum created, and there's a suction effect on the ship's bottom, and the ship sinks towards the seabed, and that is squat, if I can explain this simply. And that's why as you increase the vessel speed, and the vacuum or the suction effect on the vessel's bottom also increases, because of which the vessel sinks further towards the seabed. So you can see here when the vessel is approaching shallow water, I've try to show it by the way of diagrams. When the vessel is approaching shallow waters or confined channels, it will experience a mean bodily sinkage. When we say bodily sinkage, we mean the vessel's body sinks, and a slight trimming or a trim is experienced due to the changes in the vertical pressure forces acting on the hull. Now, the vertical pressure forces acting on the hull is what I was referring to as the Venturi effect, which basically sucks the ship's bottom. There is a suction effect, and that is the vertical force X. So squat varies in proportion to the square of the water speed, the hull shape where the block coefficient comes into play, as well as the side and the underkeel clearance. So you can see here what is happening at zero speed and what is happening when the vessel is moving forward. So you can see the full form vessels are shown, and the effect of the static trim on a full form ship's dynamic trimming in shallow water and confined waters are shown. So if zero static trim, that is even keel, the trim will be by the head due to the full form hull. So which are the full form vessels? Full form vessels are those vessels which have a block coefficient more than 0.70. Otherwise, if it's less than 0.70, they are called fine form vessels. So you can see in full form vessels, the touchdown will occur at the bow with possible damage to the forepeak tank or the bulbous bow, as you can see in the figure. So you can see there are two columns. So on the right side, we have shown you the speed moving at the forward speed, and on the left side you can see the vessel is at zero speed. Basically, the ship is not moving. So the vessel is a full form vessel on even keel, but as it starts to move, a full form vessel will likely to be trimmed by the head, and that's why there's more chances of the ship's forward part touching the bottom first and resulting in a damage. If the ship is trimmed by the stern, the trim will be further by the stern when the vessel is moving, when it's underway in flow restricted waters, and touchdown then occurs at the stern with possible damage to the rudder and propeller. So if the vessel is on even keel and when it's moving forward, there is more chances of the ship's forward to get touched, but when it is at a stern trim, there is more chances of the vessel stern to get touched in the bottom. And if the ship is trimmed by head, of course the trim will be further by the head when underway, and again the ship's forward part will get damaged, or there's possibility of the forward part touching the bottom first. All right, so you can see here that the ship's movement makes a lot of difference, and so does the trim of the vessel, and that's why in the previous slide we showed what are the factors that affects the squat. So these are the factors. When the ship is stationary, as you can see on the diagram, there is less chances of the vessel bottom getting touched due to the effect of the squat. Now we move on to tidal windows. So in certain tidal areas, adequate UKC or underkeel clearance may only be attainable or achievable when the tide is above a certain height. So you need to wait for the adequate tide for the vessel to have the required UKC for the vessel to safely sail out from the port. In such cases, the vessel must transit that area within a certain time period based on the predicted tidal heights. The time period must be clearly shown on the chart and or notes. Predicted tide heights can differ from actual heights. So here you will have a tidal window. When we say a tidal window, you basically have a few hours of a window. You basically have few hours, let's say. Let's keep it more simple in terms of language. So you have that few hours that provide you with a safety margin. That safety margin is known as the tidal window. So you have those few hours within which your ship must sail out. And to understand what are those hours, you have to carry out a calculation. So the chief officer will decide on the departure draft once he or she is aware of the cargo that is to be carried. Once you know your departure draft, then you can carry out a calculation that will tell you when it will be adequate for the vessel to sail out. Now this situation is normally faced in river passages or in ports with varying height of tide. Most of the ports otherwise they dredge the channel and keep the draft, rather keep the depth of the water sufficient for any ship to sail out. But of course you will be going into ports where you may have varying height of tides. For that you have to calculate the time during which you have a high tide or the adequate underkeel clearance, and when it will be safe for the vessel to actually sail from the port. So for tidal windows, it is frequently necessary when transiting areas of shallow water to analyze the available depth of water, not just on the time and tidal height basis, but also taking into account the vessel's likely time of arrival and departure through the area. In addition, the navigator must take into account the earliest time of arrival and the latest time of departure that the vessel may transit at a particular point. Because you have to remember that your ships should arrive and depart in time. Your company would like you to arrive and depart in time and not cause unnecessary delays. So you have to make sure that you arrive at the earliest time and you can depart at the earliest time as well. Because if you stay in the port and your calculations are not correct, and it will cause delays, it will cost the company extra money. And going back to the previous slide, you have to remember that whatever calculation you do, you must add a certain safety margin to it, because your prediction or your calculation may slightly differ from the actual situation. So make sure after you calculate, you also have a slight safety margin available to you as a master or as an officer, so that your ship is safe while arriving and departing the port. The production of a tidal window graph can be broken down into 5 stages. The first stage is the analysis of the vessel's squat characteristics. The second stage is the production of a minimum depth required, or MDR, at various speeds. The third stage is a determination of critical depth points on the chart. The fourth stage is the analysis of tidal heights at the critical points. And finally, the last stage is the production of the tidal graph window. The minimum depth required, or MDR, is calculated for a vessel by taking into account the maximum static draft of the ship, the squat, the required UKC, and remember that the MDR is to be calculated for the maneuvering speed of the vessels, because when the vessel is slowly departing the port, it will not be at its full speed, it will be at its maneuvering speed, and that is the speed that you should be taking into account when calculating the minimum depth required. All right. So here you can see is a MDR table, or a minimum depth required table, shown for a vessel at different maneuvering speeds. So you can see when the vessel is stopped at 0 knots, the squat is also 0. And here an example has been taken, of course, that the minimum depth required, which will be equal to your draft plus your UKC plus taking into account the squat, is at 11.55 meters. Alright, so UKC here is being allowed for 10% of the draft. So your UKC here is maintained as at least 10% of the draft. And then you can see as the draft or the speed is increasing from stop to dead slow ahead to slow ahead, half ahead, and full speed, you can see that the squat value is increasing as well, and so is the value of the minimum depth required, because you are adding the squat value to the minimum depth required plus having a 10% of UKC, and then the draft, of course, you can see that the minimum depth required is increasing. So you have to take into account these values and before you make any calculations. These are available from your maneuvering diagram as well. Then we talked about the critical depth. So at any point of the entire voyage where depth of water is less than the minimum depth required is considered as critical depth, because at that point of time your vessel is in a critical situation. It requires the height of tide for the vessel to pass over safely, because there will always be chances for the vessel to then touch the bottom. You need to have the minimum depth required. Of course, sometimes you take into account the safety margin. That is where the safety margin comes into play. But as soon as it is less than the minimum depth required, you have to say that the vessel is in a critical situation at that point of time. These points should be noted for each individual chart and should be highlighted with an alert on the chart itself, so that the officer on watch can make a note of these points before arrival to these points and warn the pilot or the master of these points during the passage of the vessel. All critical depths as far as half a nautical mile on either side of the track should be noted to allow for a reasonable cross-track error, because it will be hard for you to keep your vessel exactly on the track that you have decided. So naturally you must allow for the vessel for some movement, and that is why half a nautical mile on either side should be marked, because the vessel will not be exactly on the track all the time. The current will be there, the wind will be there, maybe the vessel will be altering to avoid collisions, and during the passage other factors may come into play. There could be fishing boats, so you have to allow for that margin of movement of the vessel, and that's why you should mark it on either side of the track. So the critical depth when the available depth is less than the minimum depth required, and the tidal height is required to cross over. We've talked about all this. I will not again waste time on this, but this is where I was just trying to show you if the vessel is going to pass over a danger of navigation. This is when it becomes critical, because you can see the black arrow shows the critical depth, but the circular dots horizontally shows the critical depth, which is less than the minimum depth required, and that becomes the critical point. Although the vessel may pass safely over the wreck at this point of time or danger to navigation, still it is a critical situation when the vessel's passage should be monitored carefully by the master and the officer. Then we come into the tidal heights, which can be obtained from the various tide tables and in offshore places, and can be found from co-tidal charts. I have made numerous videos on tidal calculations, and I have given you the links to those videos in the description section below. Please watch those videos on how to calculate tides for standard ports, secondary ports using simple harmonic motion, simple interpolation, and so on. But make sure here you note that the predicted tidal heights may vary due to unusual meteorological conditions. You cannot say for sure that whatever calculation you carry out based on the books is what you will experience. Sometimes they may be slightly different, and that is why I always say that you must always keep a margin of safety to ensure that your vessel is safe throughout the passage, even if it fluctuates, the depth fluctuates a little bit here and there. Once the navigator has calculated the minimum depth required for the vessel and has found the depth of water at the critical point on the chart, it is then a matter of applying the predicted height of tide for that location and finding out the tidal window, which will give you those few hours, the range of those few hours, the margin of safety for those few hours when your vessel can sail, arrive in a port. So you can see here that the tidal graph is being shown, where the predicted tidal heights for a location can be compiled into a graph form for the full day. So this will give your master, or you as an officer on watch, or if you are the master, it will give you an idea of when is it safe for the vessel to sail out with the required height of tide or with the minimum depth of water required, and that gives you the margin. So depending on what height of tide you want to sail out, or rather what minimum depth required you want to sail out with, the hours between those times will give you the tidal window. So for a vessel, for example, let me take an example here. For a vessel whose draft is about 11 meters, the following table can be compiled for the controlling depths, which are the critical depths of 11 meters, 11.3, 11.6, 12 and 12.2 meters. So here, of course, the draft of the vessel is 11 meter, and if I consider 10% of the draft to be maintained as UKC, my UKC required will be 1.1 meter. So 10% of 11 meters is 1.1 meter. Then based on the maneuvering diagram, where I have the squat values for the various speeds, I will add the draft of the vessel and the UKC plus the squat value. So the first example, you can see I have added 11 plus 1.1, which gives me 12.1 because the squat is 0. But then 11 plus 1.1 plus a squat value of 0.17 for dead slow head gives me 12.27, and similarly so on and so forth. So you can see as the speed has increased from stop to dead slow head to slow head to half ahead to sea full speed, the squat value has increased, and so has my minimum depth required. Alright, then for the various controlling depths, I have the values below for against the speeds and the height of tide calculated. So you can see that for the depth of 11 meters, 11.3, 11.6, 12 and 12.2, which refers to critical depths, I have the values given to me in terms of what is the height of tide required. So if I know the depth of the water and I know the minimum depth required, I know how much do I need for the height of tide to be for me to sail out during that time. Alright, so once on the graph, it will be seen that for a particular controlling depth, there is a fixed time during the 24-hour period that the vessel will have sufficient water to cross the depth. For a depth of 11 meters, the vessel will not have sufficient water to cross over at any time of the day, even at dead slow speed, because the squat will change with speed. In which case the vessel must either reduce the draft, it can do so by maybe deballasting operations, or take a different route. Whereas for a controlling depth of 11.3 meters and at dead slow speed, the height of tide required will be 0.97 meters. Alright, so you may have to make some adjustments where the chief officer will come into play. He might pump out some water from the ballast because that would be the only way. Other than, I don't think you can get rid of any cargo or anything like that, or you may adjust the cargo on some ships to get the draft required, but in most of the cases you will be engaging in deballasting operations if it is allowed to do so, and you will have to reduce the depth. So this was one of those cases. By drawing a line across the graph at 0.97 meters, the navigator will easily see that there is sufficient water for the vessel to cross over between, in this case, 004 hours and 1040 hours, and again between 1430 hours and 2210 hours. So the time between 0040 and 1040 gives you the tidal window, and again the time between 1430 and 2210 gives you the second tidal window. So these two timings are the tidal windows that are important to the vessel's safe crossing over the critical depth based on the minimum depth required. Alright, otherwise if maybe another experienced master may reduce the minimum depth required, maybe if he doesn't want 1.1, maybe they are happy with 70 centimeters or 50 centimeters. Like I said before, in some situations you have to sail out with lesser under keel clearance, but that depends on the situation, whether the seabed is safe, whether that is a routine. Those decisions will be taken by the master in consultation with the port authority and the pilot. So that are different situations, but here I just wanted to show you an example of what is done normally if you want to keep a 10% of the draft as the UKC. So once the tidal window has been calculated, the navigator then needs to highlight this clearly on the chart with an alert showing clearly the speed that the vessel must slow to and the timings of the tidal window. First, the ETA, or the estimated time of arrival to the critical depth, is calculated, and then a safe margin before and after is allowed for and is entered on the chart using the template that I will show you. So this is the template that I have shown you. So this is a template at which you can see that we calculate the 0R refers to the estimated time of arrival or estimated time of departure, and the time -1 and +1 tells you about the tidal conditions, 1 hour before arrival and 1 hour after arrival, or 1 hour before departure and 1 hour after departure. So 0R refers to the exact time, and then -1 and before and +1 hour is 1 hour later. That gives you some safety margin or tidal window as well. Not tidal window, but it gives you information about 1 hour before what is happening with the tide and what will happen 1 hour later, because the vessel may not exactly arrive or depart at the time that has been decided. It may arrive a little bit earlier or later, and similarly it may depart a bit earlier or later, but at least you have the information available to you on the chart in way of this template, where the time is provided and so is the depth plus tide, and the UKC that the vessel will experience during that time is provided as well. So the master or the officer on watch can make an informed decision on whether it is safe for the vessel to arrive or depart during that time. Finally, a spreadsheet may also be created by the officer on watch, and which will show the draft of the vessel, the minimum depth of the water, the tide height required, and the UKC available at any particular time. So here also the tidal window may be noted, it may be highlighted, so that it is easier for the master to make a decision when it is safe for the vessel to proceed with the minimum depth required. So I think you've got the idea. These are just examples to show you how the alert may be generated and how the alert may be shown on the charts and your passage plan. You may use some other template. It depends on your company and depends on the software that you are using as well. So I think this is pretty much it. The video has become a bit long. So I have only one more video to go regarding passage plan. That will be part 5 of the video, and after that we'll talk about, in that video I'll talk about constant radius turns and all that, and how do we use that in passage planning. So watch out for that video guys, and I'll see you soon. Bye for now.